Southern Egypt begins with a brutal contradiction: enormous water beside an enormous desert. The answer would become an artificial water corridor on a nearly unimaginable scale.
Really make the Sahara bloom?
Can Egypt really move Nile water 310 kilometers and make the Sahara bloom?
Here, summer heat can approach 50 Celsius, punishing workers, equipment, and fresh concrete.
Then sandstorms can erase roads, markers, and open excavations within a single shift.
At the intake, engineers must also build beside water tens of meters deep. Below the sand lie clay, saline aquifers, limestone, and exceptionally hard granite. Uncontrolled heat can accelerate moisture loss and drive dangerous cracking during concrete curing. Even completed excavation can disappear beneath wind-blown sand before the next morning.
So the real challenge is not digging a canal, it is controlling an entire desert.
Most Egyptians live inside a remarkably narrow strip surrounding the Nile.
Urban expansion also competes directly with some of Egypt's most valuable cultivated land.
Expanding agriculture, therefore, requires creating productive land beyond the traditional river valley. The Toshka strategy redirects Lake Nasser water toward the western desert. The wider New Valley plan envisioned a canal corridor extending roughly 310 kilometers. Water would support farms first, then roads, industries, and entirely new communities. Every hectare successfully reclaimed converts barren ground into potential food-producing infrastructure. But irrigation succeeds only when pumping, drainage, soil, power, and salinity work together. This system must function not for kilometers, but across hundreds of desert kilometers.
Before construction, we have to understand what the desert is hiding underground.
The earliest alignment begins simply. Teams establish the canal centerline stake by stake. High-precision GPS converts temporary wooden markers into a recoverable digital alignment.
When storms bury the markers, satellite coordinates allow crews to rebuild the line.
Laser scanning captures millions of elevations and exposes subtle terrain invisible from ground level. Combining satellite and ground data reveals the least disruptive route through the landscape. Next, geotechnical drilling samples the materials that will support canals, roads, and structures. Core samples reveal dramatic changes from loose sediment to competent rock.
Laboratory testing determines strength, permeability, settlement behavior, and response to added water.
Groundwater wells expose a second danger: naturally saline water beneath future farmland.
Mapping salinity shows where irrigation could mobilize buried salts toward plant roots.
Then surveyors find a harder obstruction, a granite ridge approximately 9 kilometers long.
The route now faces two enemies: rock above and salt below.
First, water must be lifted from Lake Nasser into the gravity-fed canal network. Ordinary open excavation cannot safely expose foundations beside this volume of water.
The foundation, therefore, requires a temporary barrier strong enough to hold back the lake.
That barrier must resist water pressure while crews excavate and drill inside it.
Farther west, ordinary excavation becomes painfully inefficient against intact granite.
The rock section demands controlled drilling and blasting instead of mechanical digging alone.
Concrete creates another problem. Desert heat accelerates evaporation before proper curing develops.
Lose moisture too quickly, and thermal shrinkage can fracture an otherwise sound lining. Irrigation itself changes the ground, turning firm-looking clay into weak, sticky soil. Evaporation can then pull dissolved salts upward through microscopic pores toward the root zone.
Without drainage, irrigation could eventually poison the very soil it was meant to save.
The design must solve 6 interacting failures before any farm can become sustainable. Designers first compare closed pipelines, open canals, and hybrid water distribution systems. For the main corridor, the selected strategy combines pumping with lined open-channel conveyance.
At the lake, a massive reinforced concrete pumping complex becomes the hydraulic heart.
The real Toshka pumping station was designed around 24 enormous pumping units.
Together, these machines lift Lake Nasser water high enough to enter the canal.
A reinforced concrete lining reduces seepage and protects the canal geometry.
critical lining pores shift to cooler hours to reduce thermal stress and moisture loss.
Near sensitive aquifers, a deep bentonite barrier is specified to restrict saline movement. The storyboard design extends this cutoff wall roughly 25 meters below grade.
Separate drains about 1.8 meters deep collect saline water before it rises. Center pivots spread water efficiently across vast circular fields with controlled application rates.
Only as one integrated system can these individual solutions transform the desert. Construction begins with access, because every later operation depends upon reliable desert logistics. Hundreds of machines move outward as the project develops its transportation spine. The construction plan requires hundreds of kilometers of roads linking isolated workfronts.
Remote camps provide command, maintenance, medical support, water, and heat-protected recovery areas.
Heat exposure is managed like any other engineering hazard. Measure it and control it. Early warning stations track the wind conditions that precede dangerous haboob events. Powerful lighting allows heat-sensitive operations to migrate safely into cooler nighttime shifts.
Field batching plants shorten delivery times and improve control over concrete temperature.
Distributed plants prevent concrete from spending hours traveling through extreme desert heat. Engineered laydown yards provide stable ground for oversized steel, pipe, and lifting equipment.
At the lake, cofferdam materials arrive before foundation excavation can even begin.
The empty desert has now become a functioning construction ecosystem. Meanwhile, the project's most specialized components begin life inside heavy manufacturing facilities. Corrosion-resistant alloy steel is cut precisely into pressure-containing pump components.
But rolled shells are aligned in rigid fixtures before their structural seams are welded.
Multiple weld passes build the strength required for continuous high-volume hydraulic service. Impellers are precision machined because small geometric errors become vibration at operating speed. Shaft alignment is checked to prevent bearing loads from rising during continuous operation.
Ultrasonic inspection searches beneath the weld surface for hidden discontinuities before assembly.
Critical welds receive additional non-destructive examination before inspectors release the component. Each storyboard pump module is treated as a 35-ton precision lifting operation. Large diameter steel conduits are formed, welded, measured, and prepared for protective treatment. Factory testing verifies casing integrity, shaft movement, seals, and mechanical clearances. Only assemblies meeting dimensional and inspection criteria are cleared for transport.
Approved pump modules travel by heavy transporter from fabrication yard to the lake.
Barge transport avoids difficult overland routes and delivers the heavy units directly to site.
Construction begins by driving an enormous cofferdam around the lake foundation zone.
Internal bracing converts the thin steel wall into a temporary water-retaining structure. Dewatering slowly exposes ground that had been hidden beneath Lake Nasser.
Soft material is excavated while controlled pumping keeps the working platform stable. Deep bored piles transfer the station load beyond weak near-surface lake sediments.
Steel reinforcement cages enter each bore before tremmy concrete forms the pile. Major concrete pours move into cooler night hours to control temperature development.
Embedded sensors reveal temperature gradients before thermal stress can become cracking.
Lift by lift, reinforced concrete walls rise around the pump chambers.
Each pump must now descend through the structure without striking its precision interfaces.
Lower 1 meter per minute.
Lower 1 meter per minute. Alignment matters more than speed. Laser references center each machine before the final mechanical connection is locked. Beyond the station, earth-moving crews begin shaping the main canal corridor.
Excavated material leaves as graders establish the hydraulic profile required by the design.
At the granite obstruction, production changes from earth-moving to controlled rock excavation.
Approximately 45,000 kilograms of staged charges are distributed through the storyboard blast sequence.
Time delays fracture the ridge progressively instead of releasing the entire blast simultaneously.
Broken rock is cleared and the rough channel is trimmed back to design grade. Next comes the subsurface defense, the bentonite cement cutoff barrier.
A moving slip former places the canal lining continuously, minimizing unnecessary construction joints.
Farmland drainage pipes are welded, lowered, filtered, and buried below the future root zone.
With water conveyance nearly complete, crews assemble the machinery that will distribute it. The first full irrigation trial finally puts water onto the reclaimed desert surface.
Within hours, the wet clay loses enough bearing strength for wheels to sink.
One tower settles nearly 400 millimeters, pulling the long steel structure out of alignment.
Stop rotation now! Stop rotation! Continuing now could buckle the entire irrigation span.
The problem is mechanical. Concentrated wheel loading exceeds the softened soil's capacity.
Then a second warning appears. White salt crystals gathering around young wheat.
Extreme evaporation is drawing saline groundwater upward through the soil's capillary network.
Conductivity testing confirms that root zone salinity is climbing toward damaging concentrations. Shut down the affected pivots until we understand both failures.
A billion-dollar irrigation vision now depends upon solving mud and salt together.
Liam's team begins with undisturbed cores from beneath the failed wheel path.
Once saturated, this clay loses much of the strength supporting the wheel. The fix is straightforward physics. Distribute identical weight across a larger contact area.
Dual tires nearly double the contact footprint and reduce pressure applied to soft ground.
A maximum wetness test now challenges the modified tower under worst-case field conditions.
Settlement drops sharply, confirming that the wider footprint controls the mechanical failure.
Salt requires a different response. Deep ripping interrupts the capillary pathways, moving moisture upward.
Buried drains capture saline water below the root zone and carry it away.
The deep cutoff barrier reduces lateral groundwater intrusion into the reclaimed agricultural zone. With drainage active and loading reduced, both salinity and settlement return within limits.
The hydraulic system now needs the electrical infrastructure capable of driving enormous pumps. A dedicated high-voltage substation converts incoming power into controlled feeds for the pump hall. Power electronics coordinate startup so giant motors do not shock the electrical network. Pressure sensors watch every major hydraulic section for abnormal surges or leakage.
Any dangerous pressure excursion must trigger isolation before a pipe reaches failure.
GPS guidance keeps long pivot structures tracking accurately around their circular fields. Moisture sensors prevent overwatering, conserving water while reducing renewed salinity risk. Weather alarms can park vulnerable equipment before severe sandstorms reach the site. Separate structures have finally become one monitored, controllable water delivery system. Commissioning starts slowly, verifying every mechanical, electrical, and hydraulic protection system. Individual pump runs establish baseline vibration, temperature, current, and bearing behavior. One by one, more machines join without producing unacceptable electrical or hydraulic transients. The principal trial operates 18 units, while additional machines remain available for system flexibility. Together, the pumps overcome the elevation difference and push Lake Nasser water upward.
For the first time, the completed hydraulic path carries sustained flow into the desert.
Engineers increase velocity toward the design test condition and watch every structural joint.
Leakage, displacement, and groundwater readings must remain inside commissioning limits.
The repaired irrigation system now survives wet soil loading, while subsurface drains remove salt.
Healthy roots confirm the final requirement: delivered water is producing viable agricultural soil. With commissioning complete, the Toshka water system enters full agricultural operation.
Long pivot arms now convert pumped Nile water into precisely distributed artificial rainfall. Weeks later, geometry once drawn on engineering plans becomes visible from space.
Harvest machinery now crosses land that previously supported almost no intensive agriculture.
Water, drainage, roads, power, and machinery have created an entirely new productive landscape.
With concrete, steel, water, and relentless engineering, Egypt made the desert retreat.